Hello there, and welcome to Sleepy Science Vault. Somewhere out there, in the space between what we know and what we can only imagine, there may be another version of you. Living a different life. Making different choices. Looking up at a different sky, or perhaps no sky at all. It's one of the most extraordinary ideas in all of modern science. And yet, it begins not with certainty, but with a question. The concept most people call parallel universes is usually part of a much larger framework that physicists refer to as the multiverse. The two terms are often used interchangeably in conversation, but they aren't quite the same thing. The multiverse is the broader idea, an umbrella term for the possibility that our universe is not the only one. Parallel universes would simply be what lives inside that larger picture. Distinct worlds, separate realities, each one whole and complete on its own. What makes this so fascinating is that it isn't just the stuff of science fiction. Real physicists, at real institutions, spend real careers thinking seriously about this question. And yet, and this is worth sitting with for a moment, they don't all agree. Not even close. The existence of parallel universes remains genuinely contested among the people who understand physics most deeply. For every researcher who finds the idea compelling, there is another who considers it untestable, and therefore outside the boundaries of what science can currently address. Because that's the other thing. There is, as of now, no direct experimental proof. No signal received from another universe. No observation that could only be explained by the existence of a second reality running alongside our own. The multiverse is still, in the strictest scientific sense, a hypothesis. Modern academic papers, even those written by physicists who find the idea theoretically attractive, describe it that way. As a hypothesis. As a possibility. Not as established fact. And yet the idea refuses to stay quiet. It has been alive in science fiction for decades, appearing in novels and films and television long before it became a serious topic in theoretical physics. Something about it resonates deeply with people. Maybe because it offers a kind of comfort, the sense that somewhere, somehow, things might have gone differently. That the road not taken wasn't simply abandoned, but perhaps traveled, in some other version of reality. Even without proof, the concept keeps drawing attention. Scientists return to it. Writers return to it. And perhaps most tellingly, the mathematics returns to it. Certain equations, when followed honestly to their conclusions, seem to produce other universes almost as a natural consequence. Not because physicists are forcing the idea in, but because the theories themselves appear to point that way. That's what makes the multiverse so unusual as a scientific idea. It sits right at the edge, the very frontier of what modern physics can describe and what it cannot yet confirm. It belongs to a rare category of questions that are too serious to ignore and too unresolved to settle. A place where imagination and mathematics meet, and neither one is quite sure what to do next. This is where we begin. There is something quietly humbling about standing outside on a clear night and looking up at the sky. The stars seem countless. The darkness between them seems to stretch forever. And in a sense, it does. But here is something that most people never fully consider. What we can see, even with the most powerful telescopes ever built, is not all that exists. It may not even be close. The universe we can observe has a boundary. Not a wall, not an edge in the physical sense, but a horizon, a limit set by time and light and the age of the cosmos itself. Everything we have ever seen, every galaxy, every nebula, every distant point of light captured by our greatest instruments, all of it falls within what scientists call the observable universe. And the reason that boundary exists is straightforward, even if the implications are staggering. Light travels fast, but it does not travel instantaneously. The universe has been expanding since the beginning of time, and the light from the most distant regions simply hasn't had enough time to reach us yet. Beyond a certain point, the universe becomes invisible to us, not because there's nothing there, but because the signal hasn't arrived. That boundary sits roughly 46 billion light-years away in every direction. And within it, there are hundreds of billions of galaxies, each containing hundreds of billions of stars, many of them orbited by planets of their own. It is already a number so large it becomes almost meaningless to say out loud. And yet, according to many cosmologists, all of that, everything we have ever detected or measured or theorized about from direct observation, may be only a tiny fraction of what actually exists. The full extent of the universe beyond our observable horizon is unknown. It could be vastly larger than what we can see. It could be, in principle, infinite. And once you begin to seriously consider that possibility, certain ideas start to follow naturally. Some physicists use the term Hubble volume to describe our observable region specifically, the sphere of space from which light has had time to reach us since the Big Bang. Everything outside that sphere is, for now, permanently beyond our ability to observe. Not theoretically beyond it. Actually, genuinely, completely beyond it. At least with any technology or method we currently possess. This creates one of the deepest challenges in the entire multiverse debate. A theory can be mathematically beautiful. It can be internally consistent, logically coherent, and supported by equations that have proven reliable in other contexts. And it can still be impossible to test. This is not a minor problem. Science depends, at its core, on the ability to make predictions and then check whether those predictions match reality. If another universe exists but is completely disconnected from ours, if no signal, no particle, no influence of any kind can pass between them, then its existence may be permanently outside the reach of any experiment we could ever design. Some critics of the multiverse idea hold this up as a fundamental objection. If it can't be tested, can it really be called science? Or does it belong to the realm of philosophy, fascinating, perhaps even meaningful, but ultimately beyond the scope of what physics can confirm or deny? Those who take the idea seriously don't dismiss that concern. They simply weigh it differently. Some argue that the untestability may be temporary, that future discoveries, future instruments, future theoretical breakthroughs might change what's possible to detect. Others suggest that if a theory makes correct predictions in every area where it can be tested, then its broader implications deserve to be taken seriously even when direct confirmation is out of reach. It's a genuine tension, and it runs through almost every serious discussion of the multiverse. If other universes exist and are truly separate from our own, operating according to their own physics, expanding on their own timelines, perhaps even structured around entirely different constants of nature, then there may be no bridge between us and them. No echo, no signal, no trace. They would exist in a kind of absolute isolation, real in every meaningful sense and yet completely unreachable. Some versions of the multiverse theory go even further. They suggest that the universe we inhabit could be so enormous, so far beyond the scale of what we can observe, that regions of it separated by unimaginable distances would effectively function as separate worlds. Same universe, technically, but so far apart that no information could ever travel between them. For all practical purposes, those regions would be parallel universes. Different histories. Different arrangements of matter. Different outcomes. The sheer scale required to make that possible is almost impossible to hold in the mind. But scale is not something the universe has ever been shy about. Now, when physicists try to bring some order to all of this, when they try to organize the various ways that parallel universes might theoretically exist, one of the most widely referenced frameworks belongs to a physicist named Max Tegmark. His classification system divides multiverse ideas into 4 distinct levels, each one more abstract than the last. It's a useful structure, not because everyone agrees with it, but because it gives the conversation a common language. A way to talk about very different ideas without conflating them. The first level, and in some ways the most straightforward, emerges directly from that idea of an infinite or near-infinite universe. If space goes on far enough beyond our observable horizon, and there's no particular reason it should stop at the edge of what we can see, then by sheer probability, the patterns that give rise to matter and structure and eventually life should repeat. Not metaphorically. Literally repeat. Because the number of possible arrangements of matter, while astronomically large, is still finite. And if space is infinite, or even just vast enough, those arrangements will eventually recur. Somewhere, at an almost inconceivable distance, the same configuration of particles that produced our solar system, our planet, and ultimately you, reading, listening, resting, could exist again. This is one of the most unsettling and strangely beautiful ideas in all of modern cosmology. It doesn't require new physics. It doesn't demand exotic mechanisms or speculative additions to our current understanding of the universe. It requires only what we already suspect might be true, that the universe is very, very large. Perhaps infinite. And that in an infinite space, with a finite number of possible arrangements, repetition becomes not just possible but, in a certain mathematical sense, inevitable. This is sometimes what physicists mean when they talk about the simplest kind of parallel universe. Not a dramatic rupture in the fabric of reality. Not a doorway to another dimension. Just space, continuing far beyond what we can see, eventually producing, through nothing more mysterious than probability and scale, another world very much like our own. Somewhere unimaginably far away, there may be another Earth. Another sky. Another quiet night, just like this one. let's build on what we explored before and go a little deeper. The scientific theories around parallel universes aren't a single idea. They're a collection of ideas, different in scale, different in mechanism, different in how seriously they're taken by the physics community. And one of the most useful ways to approach them is to think of them as a kind of hierarchy. A ladder of increasing strangeness. You start with something almost intuitive, something that follows almost naturally from what we already suspect about the size of the universe, and you climb, step by step, toward ideas that are genuinely difficult to hold in the mind. The first rung of that ladder is where we've already been. Level 1. The core assumption behind a Level 1 multiverse is simple. Space is effectively infinite, or at least vastly larger than the region we can observe. That's it. No exotic physics. No new forces or dimensions. Just space, continuing outward well beyond the edge of what light has had time to show us. And from that one assumption, the rest follows on its own. What's worth noting is that within Tegmark's framework, Level 1 is considered the least controversial of all the multiverse categories. Not uncontroversial, the multiverse as a whole remains a subject of genuine scientific debate, but compared to what comes later, Level 1 is almost conservative. It doesn't ask you to imagine fundamentally different laws of nature. It doesn't require a separate realm of existence or a branching of reality. It simply asks you to take seriously the possibility that the universe doesn't end where our instruments do. And in a Level 1 multiverse, the same physics applies everywhere. The same speed of light. The same gravitational constant. The same fundamental forces that govern everything from the fusion happening inside distant stars to the electrical signals moving through your nervous system right now. The rules don't change. The universe, in this picture, is not a collection of wildly different realms. It's one vast, consistent expanse, operating by the same principles throughout. What varies is not the laws, but the arrangement of things within those laws. There's something almost reassuring about that, in a way. Of course, these hypothetical twin regions of space would be extraordinarily far away. Not far in the way that other galaxies are far, or even in the way that the edge of our observable universe is far. The distances involved in a Level 1 multiverse are of a completely different order, so immense that even the word astronomical seems insufficient. The nearest region where a near duplicate of our world might statistically exist has been estimated at something like 10 to the power of 10 to the power of 28 meters away. That number isn't just large. It doesn't really have an intuitive equivalent. It's the kind of distance that requires you to simply let go of the attempt to picture it. And yet the logic holds. In an infinite universe, governed by a finite set of physical laws, the number of possible distinct configurations of matter is enormous but bounded. Every arrangement of particles in a given region of space, every possible variation on a galaxy, a planet, a biosphere, a mind, exists as one entry in a list that, while fantastically long, eventually runs out of new possibilities. In an infinite space, once that list runs out, it starts again. The same configurations reappear. The same sequences recur. This is the implication that tends to stop people. Because it doesn't just suggest that somewhere out there, a planet exists that resembles Earth in broad strokes. Some versions of the theory suggest something far more specific, that there are regions of space where a person exists who is, to the limits of physical description, identical to you. Same memories. Same face. Same thoughts moving through the same mind. Living a life that has, up to some point, unfolded in precisely the same way as yours. Other versions allow for small differences. A world where one choice went differently. A world where one event turned out another way. A version of your life that diverged at some quiet, unremarkable moment, a conversation that didn't happen, a door that was or wasn't opened, and has been following a slightly different path ever since. Whether that idea feels wonderful or deeply strange probably depends on the moment you encounter it. Now, we climb the ladder. The next set of ideas takes us somewhere different, not just farther away, but into a different kind of distance altogether. To understand it, we need to talk about something called cosmic inflation. And the remarkable thing about inflation is that it wasn't invented to produce a multiverse. It was invented to solve a completely different set of problems. In the early 1980s, physicists were wrestling with several puzzling features of the universe. The cosmos, observed across vast distances, is almost perfectly uniform in temperature and structure, far more uniform than should be possible if every region had simply been evolving independently since the Big Bang. Different parts of the universe that should never have been in contact with each other look almost identical. Why? There was also a problem with the geometry of space. Observations suggested it was almost perfectly flat, and explaining that flatness required conditions at the universe's birth that seemed extraordinarily fine-tuned. Inflation was proposed as a solution. The idea, in essence, was that in the very first fraction of a second after the Big Bang, the universe underwent a period of explosive expansion, far faster than the speed of light, stretching space itself at a rate that dwarfs anything we observe today. This sudden, dramatic expansion would have smoothed out irregularities, explained the uniformity, and naturally produced the flat geometry we observe. The theory was elegant. It made predictions, and those predictions matched observations. Inflation became one of the most successful and widely accepted ideas in modern cosmology. But it brought something unexpected with it. Because inflation, when you follow its mathematics carefully, doesn't necessarily stop everywhere at once. The mechanism that drives it, a field of energy permeating space, can behave differently in different regions. In some places, inflation ends, and the energy converts into matter and radiation, producing a universe something like ours. But in other regions, inflation continues. Space keeps expanding at that extraordinary rate, driving those regions further and further beyond any possible horizon. And within that still inflating background, new regions can stop inflating, each one collapsing into its own pocket of space, its own self-contained universe, with its own properties. The image that physicists sometimes use for this is bubbles. Imagine a vast, churning medium, not water, but something more like the fabric of space itself in an extreme state, and within it, bubbles forming. Each bubble is a universe. Ours is one of them. Others form elsewhere, separated from us not just by distance but by the structure of the inflating space between them. That space is expanding so rapidly that the bubbles can never reach each other. They exist in permanent isolation, each one a closed system with its own beginning, its own physics, its own future. This is what some cosmologists call eternal inflation. And its implications are profound. If inflation truly continues forever in the wider background, driven by the same quantum fluctuations that govern the behavior of particles at the smallest scales, then the production of new bubble universes never stops. New pockets of space keep forming, keep expanding, keep evolving. The multiverse in this picture is not a finite collection of worlds but an endlessly growing one. A process still happening, right now, somewhere beyond any horizon we could ever reach. What makes this particularly significant is that these bubble universes don't necessarily share the same physical constants as our own. In our universe, the strength of gravity, the mass of an electron, the speed of light, these values are fixed. But in some theoretical frameworks, the values that emerge when inflation ends and a universe crystallizes into its final form can depend on conditions that vary from bubble to bubble. Different universes might have different versions of the fundamental constants, different rules, different chemistry, different possibilities for structure and complexity and life. Some of those universes, with slightly different constants, might be entirely incapable of producing anything complex. Stars might not form. Atoms might not hold together. Others might be rich with structure we can't imagine, governed by physics we have no framework to describe. Our universe, the one that produced stars and carbon and oceans and minds capable of wondering about all of this, sits somewhere in that landscape. Perhaps not unique. Perhaps not special in any grand cosmic sense. Just one bubble among an unknowable number of others, each one following its own path through time. That idea, perhaps more than any other in this entire subject, has a way of making the night feel very quiet. There's a moment in almost every deep scientific idea where the mathematics stops feeling abstract and starts feeling almost personal. Where a concept that began as an equation on a page quietly expands into something that touches the way you see the world. The Level 2 multiverse is one of those ideas. And to understand what makes it so different from what we've explored before, it helps to start with what it shares, and then follow it to where it diverges. We've already spent time with the idea of eternal inflation. The notion that our universe may be one bubble in a vast, perhaps endless, churning medium of inflating space. That inflation doesn't stop everywhere at once, but continues in the background while individual regions collapse into their own pocket universes, each one sealed off from the others by the relentless expansion of the space between them. That picture of our cosmos as one bubble among many is the foundation of the Level 2 multiverse. But what Level 2 adds, what makes it a genuinely different category from Level 1, is the possibility that those other bubbles aren't just faraway versions of our own universe. They may be fundamentally different in ways that go far deeper than geography. In a Level 2 multiverse, the other universes produced by eternal inflation can differ from ours not just in the arrangement of matter, not just in whether a particular star formed here rather than there, but in the very parameters that define what matter is. The physical constants. Those numbers that sit at the foundation of all physics, the ones that seem fixed and universal from our perspective, may not be universal at all in a larger sense. They may be local. Properties of our bubble. Values that happen to crystallize the way they did when our particular region of inflating space settled into its final form, and that could just as easily have settled differently somewhere else. Take a moment to consider what that actually means. The strength of gravity in our universe is a specific value. Not a round number, not something that falls out of an obvious equation, just a measured constant that appears in the mathematics of how masses attract each other. The mass of an electron is another. The strength of the electromagnetic force. The cosmological constant, which governs the large-scale expansion of space. These values are the backdrop of everything. They determine whether hydrogen forms, whether stars can ignite, whether carbon atoms are stable, whether chemistry is possible at all. Life as we know it depends on these numbers being within a remarkably narrow range. Adjust any one of them by more than a small fraction, and the universe as we understand it would look completely different, or would contain no structure whatsoever. In our universe, these constants have the values they have. And we are here because they do. But in a level 2 multiverse, those values aren't fixed across all of reality. They're outcomes. Products of the specific way inflation ended in a given bubble. Different bubbles, different outcomes. A universe where gravity is slightly stronger, where electrons are heavier, where the cosmological constant pushes space apart at a different rate. Each one self-consistent, each one following its own internal logic, but potentially completely unlike ours in the phenomena it can support. Some of those universes would be almost entirely inert. Space would expand too fast for matter to clump together. Or it would collapse back on itself before anything complex could form. Stars wouldn't ignite. Elements heavier than hydrogen might never exist. Others might produce a wild excess of black holes, or universes so densely packed with radiation that no stable structures could persist. The range of what's theoretically possible, across all the bubbles that eternal inflation might produce, is staggering. Most of it, perhaps, leads nowhere in particular. And then, occasionally, a bubble forms where the constants fall into the narrow range that allows something remarkable to happen. Atoms form. Stars burn for billions of years. Elements are forged in those stellar furnaces and scattered across space. Planets coalesce. And eventually, on at least one of them, something begins to wonder about its own existence. This is sometimes connected to what's called the anthropic principle, the observation that we can only find ourselves in a universe capable of producing us. It sounds almost circular at first. Of course we're in a universe that supports life, how else would we be here to notice? But in the context of the level 2 multiverse, it takes on real weight. If most bubble universes are barren by nature of their constants, then our universe's apparent fine-tuning isn't a cosmic coincidence requiring explanation. It's a selection effect. We are, by necessity, in one of the rare bubbles where the numbers work. Not because ours was designed that way. not because someone turned the dials to just the right settings, but because the bubbles where the dials are set differently produced nothing capable of asking the question. It's a subtle shift in perspective, but it changes everything about how the problem feels. Now, level 2 goes further still. Because in some versions of these inflation-based models, the differences between bubble universes don't stop at the constants. They extend to something even more fundamental, the number of dimensions of space itself. Our universe has 3 spatial dimensions: up and down, left and right, forward and back. That's the geometry within which everything we've ever experienced unfolds. But there's no deep mathematical reason why space has to have 3 dimensions. The equations of string theory, for example, which provides one of the theoretical frameworks in which the multiverse becomes particularly natural, describe a universe with many more dimensions than 3, most of them curled up at scales far too small to detect. How those extra dimensions are arranged and compacted determines what the low-energy physics of a given universe looks like. And different arrangements produce different physics. In this picture, the variety between bubble universes isn't just quantitative, not just a matter of gravity being stronger here, weaker there. It can be qualitative. Universes with genuinely different geometries of space, different numbers of forces, different types of particles, different rules at so fundamental a level that there may be no common language between them. Each universe, in this framework, would begin with its own initial conditions as well. Not just different constants, but a different starting state, a different distribution of energy, a different geometry at the moment of formation, a different set of seeds from which all subsequent structure would grow. 2 bubbles with identical constants might still evolve along completely different trajectories simply because they began differently. The range of possible histories, across an eternally inflating multiverse producing an endless stream of new bubbles, each one with its own constants and its own beginning, becomes so vast that it's genuinely difficult to say whether any meaningful limit exists at all. And through all of this, the bubbles remain unreachable. Not unreachable in the way that a distant galaxy is unreachable, far, but theoretically approachable given enough time and technology. Unreachable in a more absolute sense. The inflating space between bubbles expands faster than anything could travel through it. There is no path between them. No signal that could cross. If another bubble universe exists, even one right next to ours in some abstract sense of the word, we could spend the entire remaining lifetime of our cosmos sending a message toward it, and that message would never arrive. The gap would only grow. That's what makes level 2 so philosophically striking as a scientific idea. It proposes a reality of genuine, perhaps infinite, diversity, universes with different physics, different dimensions, different possibilities, and then places every single one of them permanently beyond our reach. We can reason about them. We can build mathematical frameworks that suggest they exist. We can find traces of their logic in the behavior of our own universe. But we can never visit, never observe, never confirm. It is, in a very real sense, a theory about things that can never be seen. And yet here we are, thinking about it. Drawn to the edges of what's knowable, looking out into a darkness that may contain more worlds than we have any way to count. There's something deeply human about that impulse. To stand at the limit of what can be known, and keep looking anyway. We've been thinking large. Cosmically large. Universes born from the mathematics of inflation, bubble worlds sealed off by expanding space, realms where the constants of nature take on different values and produce entirely different kinds of reality. It's a picture built on the grandest possible scale, the structure of space itself as the canvas. But now we turn the lens around completely. Because some of the most serious thinking about parallel worlds doesn't come from cosmology at all. It comes from the smallest scales in nature. From the strange, counterintuitive behavior of particles so tiny that the very act of observing them changes what they do. The quantum world. And the parallel universe ideas that emerge from it are different in almost every way from what we've explored so far, different in origin, different in structure, and different in what they actually claim about the nature of reality. Before we go there, though, it's worth spending a little more time with what we've just left behind. Because the Level 2 picture raises a question that sits at the heart of a very old debate in science and philosophy. Consider what we mean when we say that our universe appears finely tuned for life. The physical constants we've talked about, gravity, electromagnetism, the masses of fundamental particles, the energy density of empty space, are not values that drop out of any obvious first principle. They are measured. We observe them, we record them, and we find that they sit in a remarkably narrow range that permits the existence of complex structure. Change the strength of the strong nuclear force by a few percent in carbon, the backbone of all known biology, might not form in stellar interiors. Change the cosmological constant by a modest amount and space might expand so rapidly that matter never has time to clump into galaxies. The numbers look, from a certain angle, as though they were set with something specific in mind. This has troubled physicists and philosophers for decades. Some find in it a suggestion of design, that the universe's parameters were chosen. Others resist that conclusion entirely and look for a natural explanation. And one of the most natural explanations available, if you accept the framework of eternal inflation and a Level 2 multiverse, is simply that there are vastly many universes, each with different constants, and we are in one of the rare ones where the values fall in the range that permits something like us to exist. No design required. No choosing. Just an enormous, perhaps infinite, landscape of possibilities, and the simple fact that observers can only find themselves in the subset of that landscape where observers are possible. Whether that explanation feels satisfying or unsatisfying is, in some ways, a matter of temperament. Some physicists find it elegant, a clean dissolution of what seemed like a profound mystery. Others find it troubling, because it relies on the existence of things that can never be observed, and because it seems to place important explanatory weight on our own existence as the starting point. The debate continues. It will probably continue for a long time. What's clear is that the multiverse, in its Level 2 form, is not just an idle speculation. It connects to real theoretical frameworks, inflation, string theory, the behavior of quantum fields at extreme energies, that make independent predictions and have genuine scientific standing. the multiverse isn't smuggled in as an afterthought. In some approaches, it's a consequence. A thing that falls out of the mathematics whether you wanted it or not. And the image it leaves behind is worth holding for a moment before we move on. Bubble universes, each one a closed system. Each one expanding into its own future. Separated from every other by space that grows faster than anything could cross it. An ocean of inflating vacuum, foaming with the birth of new realities, each one different, each one entire, each one unreachable. It is one of the quieter, stranger facts about our moment in history that this kind of idea can be taken seriously. That it appears in peer-reviewed journals. That careers are built around understanding it. That the mathematics, followed honestly, seems at least sometimes to point in this direction. We live in an unusual time for thinking about reality. Now, the quantum world. To understand where quantum parallel universes come from, you have to start with a problem. A genuine, unresolved, deeply strange problem that has been sitting at the center of physics for nearly a century. It goes by the name of the measurement problem, and it begins with an observation that is still, if you look at it squarely, quite difficult to accept. Quantum mechanics, the theory that describes the behavior of particles at the smallest scales, is extraordinarily successful. It is, by some measures, the most precisely tested scientific theory ever devised. Its predictions have been confirmed to an accuracy that is simply remarkable. And yet, embedded within it is something that nobody fully agrees on how to interpret. Because the mathematics of quantum mechanics doesn't just describe where a particle is or what it's doing. It describes a superposition, a combination of multiple possible states, all existing simultaneously, each one with a certain probability weight, until the moment a measurement is made. Before measurement, a particle doesn't have a definite position. It has a wave function, a mathematical object that encodes the probabilities of finding it in various places. The wave function evolves smoothly and predictably according to the equations. But when a measurement occurs, something changes. The superposition appears to collapse. One outcome is realized. The particle is here, not there. The wave function, in the standard story, snaps from a spread of possibilities into a single actuality. The problem is that the equations of quantum mechanics don't actually contain this collapse. The mathematics just keeps evolving, smoothly, linearly, without any sudden jump. The collapse is something added on top, as an interpretive layer, to account for the fact that we always see definite outcomes. But what causes it? When exactly does it happen? And what becomes of all the other possibilities, the ones that weren't realized? Different interpretations of quantum mechanics answer these questions differently. Some say the wave function is just a tool for calculating probabilities, and that asking what it is beyond that is a mistake. Others propose hidden variables, additional structure beneath the quantum equations that determines outcomes in advance. And then there is a third approach, proposed in the 1950s by a physicist named Hugh Everett, that takes the mathematics at absolute face value and refuses to add anything to it. Everett's proposal is what we now call the many worlds interpretation. And its central claim is as simple as it is staggering. The wave function never collapses. the superposition never resolves into a single outcome. Every possibility that the mathematics describes is realized. When a quantum measurement occurs, reality doesn't choose one result and discard the others. Instead, it branches. All outcomes happen. Each one is real. Each one continues forward as its own version of reality, evolving independently from that point on. What we experience as a definite outcome, the particle being here, is simply what one branch of the wave function looks like from the inside. Other branches, with other outcomes, also exist. We simply have no access to them, not because they've been destroyed, but because the branching process prevents any interaction between them. Now here's what makes this different from everything we've talked about before. Those other branches, those other versions of reality, are not somewhere else in space. They're not bubble universes formed by inflation in some distant region of the cosmos. They don't exist at a cosmological distance or in a different region of the multiverse landscape. In the many worlds interpretation, parallel realities exist in a different sense entirely. They are branches of the same wave function. Separate strands of the same quantum state, occupying what physicists sometimes call Hilbert space, a mathematical space of possibilities, not a physical location you could point to. There is no distance to travel, no horizon to cross. The other versions of reality that quantum branching produces are, in a precise technical sense, right here, overlapping with the world we experience, undetectable not because they're far away but because the structure of quantum mechanics itself prevents any signal from passing between branches once they've separated. This is not a minor distinction. It means the many worlds multiverse is a completely different kind of thing from a cosmological multiverse. One is about geography, other regions of space with different conditions. The other is about the structure of quantum reality itself, a branching tree of outcomes, growing at every moment as quantum events resolve into their various possibilities throughout the universe. And the branching doesn't happen only in laboratories during deliberate experiments. It happens constantly, everywhere, at every scale at which quantum processes occur. Which is to say, it happens everywhere, always. Every radioactive decay that either does or doesn't happen in a given moment. Every photon that either passes through a filter or doesn't. Every quantum fluctuation in every particle and every atom of every object in the universe. If the many worlds interpretation is correct, all of these events are branching points. And the number of branches being produced, at every moment, is so vast as to be essentially incomprehensible. The universe, in this picture, is not a single history. It is a continuously expanding tree of histories, each one as real as any other, each one containing observers who believe, correctly, from their perspective, that they are experiencing the one true timeline. It is, by any measure, one of the most radical ideas in the history of science. And it has the unusual property of requiring no new physics, no extra assumptions, no modifications to the equations. It takes quantum mechanics exactly as it is, and simply refuses to flinch at what the mathematics implies. Whether it's right is another matter. But it has been taken seriously by serious physicists for decades. And once it's been considered, once that image of a branching, endlessly multiplying reality has settled in, it becomes a surprisingly difficult idea to entirely put down. What does it actually mean for every quantum possibility to become real? It's the kind of question that sounds almost too large to approach directly. So let's come at it gently, from a specific angle. Think about a single quantum event, one of the simplest kinds. A radioactive atom, sitting quietly, with some probability of decaying in the next second. Standard quantum mechanics assigns that atom a wave function that evolves over time, a spreading, blending mathematical description that holds both possibilities simultaneously. The atom has decayed. The atom has not decayed. Both states are present in the mathematics, weighted by their respective probabilities, right up until a measurement is made. In the standard story, measurement collapses this to one outcome. Either the atom decayed, or it didn't. One possibility survives. The other vanishes. In the many worlds picture, nothing vanishes. Both outcomes continue. The branch in which the atom decayed proceeds forward in time, carrying everything that was entangled with that event, the detector that registered it, the air molecules that were disturbed, the person who noticed, the chain of consequences spreading outward from that single quantum moment. And the branch in which the atom did not decay proceeds equally forward, equally complete, equally real, carrying its own unbroken chain of consequences into the future. Neither branch knows about the other. Neither can detect the other. From the inside, each one looks and feels exactly like a single, definite, continuous reality. Observers in each branch remember a consistent history. They have no access to the alternatives, not because the alternatives were erased, but because the branching itself creates a kind of absolute separation. The two branches decohere. They stop interfering with each other, and from that point on, for all practical purposes, they might as well be separate universes. This is what many worlds is actually saying. Not that quantum events make the universe shimmer or flicker between states. Not that there's some ghostly superposition hovering over everyday life. But that the wave function, the complete quantum description of reality, simply keeps evolving, splitting into distinct branches at every quantum juncture, each branch carrying forward a fully realized version of events. And those branches don't go anywhere. They don't separate into distant regions of space. They occupy what physicists call the same space and time as each other, in the sense that they all emerge from the same underlying wave function. They're not bubbles drifting apart through an inflating cosmos. They're more like overtones, distinct frequencies that coexist in the same medium, each one coherent in itself, each one running in parallel with all the others without any of them being able to hear the rest. This is what places the many worlds interpretation in its own category in Tegmark's framework, Level 3. And what Level 3 is often noted for, among physicists who discuss it, is something that might seem surprising at first. It adds no new physics. None. It doesn't require a new force, a new field, a new dimension, a new constant. It takes the equations of quantum mechanics exactly as they are, with all the same particles and all the same interactions, and simply removes the assumption that measurement causes collapse. Everything else follows from that one change, or rather, from that one refusal to add something extra. In that sense, the many worlds interpretation is almost austere. It's a minimalist position. Where other interpretations add hidden variables or special rules for measurement, many worlds says only, trust the mathematics. Follow it wherever it leads. And where it leads, apparently, is to an endlessly branching tree of realities, all of them equally described by the same fundamental equations, all of them unfolding from the same quantum origins. Of course, that austerity comes at a cost. Because what many worlds takes away in additional assumptions, it pays back in sheer ontological weight. The number of branches implied by constant quantum branching across the entire universe is a number that doesn't really have a name. Every quantum event in every particle everywhere, at every moment, each one a potential branching point, each one multiplying the number of coexisting realities. The scale of it makes the level 1 and level 2 multiverses, vast as they are, seem almost manageable by comparison. Some physicists find this deeply uncomfortable. Not because the math doesn't work, it does, but because the idea of an uncountable proliferation of equally real universes seems to strain against something intuitive about parsimony. Why multiply realities so extravagantly if you don't have to? Others argue the opposite, that removing the mysterious and ill-defined collapse process is itself the more economical move. That a single clean rule, the wave function always evolves, is simpler than a theory that invokes something different and unexplained at the moment of measurement. The debate between these positions has been ongoing for decades and shows no sign of resolving cleanly. But here is something worth holding on to, because it's easy to miss in the abstract language. The many worlds interpretation doesn't say the universe literally splits. Not in the physical sense of something tearing apart. There's no catastrophic rupture, no dramatic division, no moment at which reality cracks down the middle. The branching is a feature of the wave function, of the mathematical description, a gradual, continuous process of decoherence through which different components of a quantum state stop interfering with each other and begin evolving independently. It happens quietly, at scales far below anything directly perceptible. You wouldn't feel it. You couldn't feel it. The universe, from the inside, looks and feels like one continuous, singular reality, and that appearance is entirely consistent with the many worlds picture, because each branch produces exactly that impression for the observers within it. What this means for the nature of identity, of choice, of experience, these are questions that extend well beyond physics. If every quantum possibility becomes real, then somewhere in the branching structure of level 3, every outcome you've ever been uncertain about has a branch where it went differently. Every decision that felt genuinely open, every moment that seemed to hang suspended between possibilities, resolved, in this picture, into all of its possibilities, each one real, each one inhabited by a version of you who is as continuous with your history as you are. It's a thought that arrives quietly and then refuses to leave. The branches don't communicate. The versions of you living in them don't know about each other. But in the structure of the wave function, in the mathematics that describes reality at its most fundamental level, they are there, running forward through time in their own separate tracks, each one convinced of its own continuity, each one unable to imagine the others. Level 3 is, in many ways, the most intimate of the multiverse proposals. It doesn't place other realities at cosmological distances or in a separate inflating background. It places them, in a sense, in the same moment, woven into the same quantum fabric, arising from the same physical event, diverging at the speed of decoherence, becoming unreachable not by distance but by the structure of quantum mechanics itself. Close, in a way that has no practical meaning, and unreachable, in a way that is absolute. There's a version of the multiverse conversation that stays safely abstract, universes as distant mathematical objects, parallel realities as theoretical constructs with no particular bearing on anything we might actually care about. And then there's a different version of the conversation, one that some physicists find surprisingly compelling, where the multiverse stops being purely philosophical and starts looking, at least from a certain angle, almost practical. It begins with a question about decisions. In the many worlds picture, every quantum event that has more than one possible outcome produces a branch for each possibility. That much we've already explored. But there's a version of this idea that extends the branching framework beyond the laboratory and into the texture of everyday life, into the moments where things feel genuinely open, where a choice or a chance could go more than one way. Some interpretations suggest that decisions themselves, to the extent that they involve quantum-level processes in the brain or in the physical world, contribute to branching. That every genuinely open outcome becomes real somewhere in the structure of the wave function. If that's true, then the multiverse isn't just a feature of particle physics experiments. It's a feature of every morning, every conversation, every moment that felt like it could have gone differently. Because in this picture, it did go differently. Every path that was genuinely available was taken, in some branch. The one you're in is simply the one your particular thread of the wave function followed. Whether that's comforting or disorienting probably depends on the moment. But it's worth sitting with, because it changes the texture of the idea. The multiverse, in this framing, is not something remote and theoretical. It is, if the interpretation is correct, woven into the fabric of ordinary experience. Now, some researchers have taken the many worlds idea and pushed it in a direction that might seem unexpected. They've argued that the multiverse isn't just a philosophical consequence of quantum mechanics, it may have something to do with why quantum computing works at all. Quantum computers are real devices. They exist, they function, and they can solve certain categories of problems far faster than any classical computer could. The reason, at least in broad outline, is that quantum systems can exist in superpositions, holding multiple states simultaneously, and quantum algorithms are designed to exploit that property, exploring many possibilities in parallel before converging on an answer. It's a genuine computational advantage, and it's been demonstrated experimentally. The question of why quantum computers can do this is where the multiverse enters. Some physicists, David Deutsch, one of the pioneers of quantum computing, is among the most prominent, have argued that the many worlds interpretation provides the most natural explanation. In Deutsch's view, when a quantum computer performs a calculation, it is literally doing so across multiple branches of the wave function simultaneously. The parallel processing isn't a metaphor. It's a physical reality. The computation is distributed across what are, in effect, parallel universes, and the answer emerges from the interference between those branches. In this framing, the multiverse is not just an interpretation of quantum mechanics. It is, in some sense, a resource. A substrate of parallel realities that quantum algorithms can exploit, at least indirectly, through the mathematics of interference. The fact that quantum computers outperform classical ones on certain problems is, on this view, evidence, not proof, but suggestive evidence, that those parallel computational strands are real. Others are more cautious. The same quantum algorithms can be described and explained without invoking the many worlds interpretation. The mathematics works regardless of which interpretation you prefer. But the image is striking nonetheless, that the machines we've built to harness the strange power of quantum superposition might be drawing, in however abstract a sense, on the resources of parallel worlds. It's a thought that sits at the intersection of the deeply theoretical and the surprisingly concrete. And it's one of the reasons that the many worlds interpretation continues to attract serious attention, not just as a philosophical position but as a potentially meaningful framework for understanding what quantum mechanics is actually doing. With that, we've reached the edge of the more familiar multiverse territory. Level 1, Level 2, Level 3, each one strange in its own way, each one grounded in physical theories that have genuine scientific standing. But now the landscape shifts. Because there are ideas about parallel universes that go further still, that depart more radically from our everyday intuitions about space and reality, and they come from some of the most ambitious theoretical frameworks in all of modern physics. String theory is one of them. String theory began as an attempt to unify the two great pillars of modern physics, quantum mechanics and general relativity, which are extraordinarily successful individually and deeply incompatible with each other at their foundations. Quantum mechanics governs the very small. General relativity governs the very large. Both are confirmed by experiment to remarkable precision. And yet, when you try to combine them, the mathematics breaks down. String theory proposes a resolution, a framework in which the fundamental constituents of nature are not point particles but tiny, vibrating strings of energy, and in which the universe has more dimensions than the 3 of space and 1 of time we're familiar with. 10 dimensions, or 11, depending on the version. The extra ones are curled up at scales so small that they have no observable effect at the energies we can probe. Within string theory, a landscape of possible universes emerges, an enormous number of different ways the extra dimensions can be arranged and compacted, each one corresponding to a different set of physical laws. That number is often cited as something like 10 to the power of 500. Not 500. 10 to the power of 500. A number so far beyond ordinary comprehension that it makes the word enormous feel completely inadequate. Each entry in that landscape is a self-consistent set of physics, a possible universe with its own constants, its own forces, its own possibilities for structure and complexity. String theory doesn't by itself say that all these universes exist. But combine it with the framework of eternal inflation, where different bubble universes can crystallize with different physical properties, and the string landscape provides a vast menu of possible outcomes for those bubbles to land on. The combination is sometimes called the string landscape multiverse, and it's one of the most discussed and most contested ideas at the frontier of theoretical physics. Then there are the braneworld scenarios. In certain versions of string theory and its extensions, the extra dimensions of space aren't just curled up and hidden. They can be large. And within those large extra dimensions, our universe may be a membrane, a brain, in the technical language, a three-dimensional surface floating in a higher dimensional space. Everything we've ever observed, every particle, every force, every structure in the cosmos, would be confined to this membrane. We couldn't leave it. We couldn't directly detect what lies beyond it. But other brains might exist, parallel to ours, separated not by ordinary distance but by extent in a dimension we have no access to. The separation between our brain and a neighboring one might be extraordinarily small in that extra dimension, smaller, perhaps, than an atomic nucleus, and yet completely unreachable. Because the particles and forces that make up everything we know are locked to our membrane. Only gravity, in some of these models, can leak between brains. Only the weakest of the fundamental forces can escape the surface we're confined to. Which would mean that the influence of another universe might be felt, in principle, through gravitational effects, a faint, detectable signature of a parallel world pressing against ours across a gap that has no name in ordinary geometry. Whether those effects have ever been observed, or could be, is a question that remains genuinely open. From braneworlds, we arrive at the ekpyrotic model. And this one rewrites not just the structure of space but the story of time. The ekpyrotic scenario proposes that what we call the Big Bang, the event we treat as the beginning of everything, was not a beginning at all. It was a collision. Two brains, moving through a higher dimensional space, drifting toward each other across that extra dimension, eventually meeting in a catastrophic impact. The energy of that collision flooded the brains with heat and radiation, producing the hot, dense state that we observe as the early universe. And the process may be cyclical, the brains separating after the collision, cooling, eventually drifting back together, colliding again, producing another Big Bang, another universe, another cycle of cosmic time. An endless rhythm of creation and dissolution, playing out across a higher dimensional stage that our instruments can never directly see. It is one of the more haunting images in theoretical cosmology. That our universe, with all its billions of years of history, all its billions of galaxies and all the life they may contain, is one beat in an eternal pulse. One collision in a sequence that has neither beginning nor end. And then there are black holes. Some models propose that universes can form inside black holes. That when a sufficient quantity of matter collapses beyond a certain point, the conditions created in the interior might trigger something like a new inflationary expansion, a new universe, budding off from ours, growing into its own space and time on the far side of a singularity. A universe that shares no ordinary space-time connection with the one that produced it, but that might carry some inherited properties, slightly modified physical constants, passed along through the gravitational collapse the way traits are passed between generations. This idea, associated most prominently with the physicist Lee Smolin, suggests a kind of cosmic natural selection. Universes that produced more black holes produced more offspring universes, each one slightly varied. Over many generations, the distribution of universes would shift toward those with physical constants that favor black hole formation. And the constants that favor black hole formation also happen to favor the formation of stars, heavy elements, and complex chemistry. It is speculative in the extreme, but it has a property that most multiverse ideas lack: it makes testable predictions. If cosmological natural selection is correct, our universe's constants should be near optimal for black hole production. That's a claim that can, at least in principle, be checked. We've come a long way from the simple observation that space might be infinite. From level 1's vast repetitions, to inflation's bubble worlds, to quantum branching's intimate parallel strands, to string landscapes and colliding brains in universes born inside black holes, the landscape of multiverse ideas is genuinely diverse. Each one emerging from a different corner of theoretical physics. Each one strange in its own particular way. Each one asking us to hold a slightly different picture of what reality might, at its largest and most fundamental scale, actually be. The night is deep. The questions are deeper. And somehow, that feels exactly right. We've been following a thread that started with space being very large, and has led us, step by step, to some of the most ambitious ideas in all of modern physics. Each level of the multiverse framework has asked a little more of our imagination, a little more willingness to let go of what feels intuitively obvious and follow the logic wherever it leads. But nothing we've encountered so far quite prepares you for where the thread goes next. Level 4 is different in kind, not just in degree. To understand why, it helps to notice something about everything we've discussed so far. Level 1, Level 2, Level 3, and all the braneworld and black hole scenarios share a common assumption. They assume that the other universes, however different from ours, are still physical. They exist in some kind of space. They evolve through some kind of time. They are made of something, governed by something, even if that something is a different set of constants or a different configuration of extra dimensions. The framework, however exotic, is still fundamentally a physical one. Level 4 abandons that assumption entirely. The proposal at the heart of Level 4 is this: that every mathematically consistent structure exists, not as an abstract object in some philosopher's mind, not as a description of something real, but as a genuine, concrete reality in its own right. That mathematical existence and physical existence are, at the deepest level, the same thing. That there is no separate step between a mathematical structure being coherent and it being real. If the equations are consistent, the universe they describe is out there. This is Max Tegmark's mathematical universe hypothesis, what he calls the ultimate ensemble. And it is, by his own acknowledgement, the most radical and controversial of the multiverse proposals. Because it doesn't just expand the number of universes. It changes what we mean by the word real. Think about what this implies. Our universe can be described mathematically. Its laws are encoded in equations. Its particles and fields and the relationships between them can be expressed in mathematical language with extraordinary precision. Tegmark's hypothesis says that this isn't a coincidence, and it isn't just a useful tool. It says the universe is a mathematical structure. Not that it follows mathematical rules, that it is, at its core, a mathematical object. And every other mathematical object that is internally consistent is equally real, equally exists, in the same fundamental sense. The number of such structures is incomprehensibly large. Infinitely large. Every geometry, every set of axioms, every consistent logical framework, each one describes a universe that exists just as concretely as ours. Universes with completely different mathematics underlying them, not just different constants or different dimensions, but different logical foundations, different relationships between quantities, different notions of what space or time or causality even mean, if those concepts appear at all. Ours is one such structure, one in which the particular mathematics that governs quantum fields and space-time geometry happens to produce stars and planets and minds capable of doing mathematics. We are, in a sense, the universe becoming aware of its own mathematical nature. It is a beautiful idea. It is also, as Tegmark freely admits, extraordinarily difficult to test, and it attracts significant skepticism even from physicists who are otherwise open to multiverse ideas. Because it is not really a physical theory in the conventional sense. It's a philosophical position about the nature of existence, one that happens to have interesting implications for physics, but that doesn't make new predictions in the way that, say, inflation theory does. A related idea, sometimes called the principle of mathematical democracy, makes a slightly different but deeply connected claim. That there is no reason to privilege our particular mathematical structure over any other. That if our universe is real because it's mathematically describable, then every other consistent mathematical structure has an equal claim to reality. There is no cosmic selection criterion. No reason why this set of equations gets to describe something that exists while another, equally consistent set, describes only an abstraction. Either all of them are real, or we need an explanation for why ours was chosen, and in the absence of such an explanation, the more consistent position may be that all of them are. The implications spiral outward in every direction. Universes governed by entirely different logics. Universes where the concept of space has no analog. Universes where time is not linear, or not present at all. Universes so alien that the word universe barely applies. All of it real, in the same sense that our cosmos is real, simply because the mathematics that describes it is coherent. Whether that's a profound insight or a step too far beyond what science can meaningfully address is a question that reasonable people disagree about sharply. And that brings us, naturally, to the criticisms. Because for all the elegance and ambition of multiverse theories, at every level, from the simplest to the most radical, there is a substantial and serious body of objection. Not from people who haven't understood the ideas. From physicists and philosophers who have thought about them carefully and found them wanting in specific, articulable ways. The first and most persistent objection is one we've touched on throughout, the problem of testability. Science progresses through a cycle of prediction and verification. A theory makes a claim about how the world is, and that claim is checked against observation. If the claim holds up, confidence in the theory grows. If it fails, the theory is revised or abandoned. This process is what distinguishes scientific knowledge from other kinds of knowledge, and it has proven remarkably successful. Multiverse theories, across most of their forms, struggle to make predictions that can be checked in this way. If other universes are separated from ours by space expanding faster than light, or by the structure of quantum decoherence, or by dimensions we have no access to, then they produce no observable signal. Their existence, or non-existence, leaves no trace we can detect. And a theory that predicts something undetectable is, in the strictest sense, not doing what scientific theories are supposed to do. Some physicists consider this a temporary limitation, a gap that future theoretical or observational advances might close. Others consider it a fundamental problem, one that places multiverse theories outside the domain of science as it is currently understood. The philosopher Karl Popper's criterion of falsifiability, the idea that a genuinely scientific claim must be capable of being proven wrong, is often invoked here. If no conceivable observation could distinguish between a universe with a multiverse and a universe without one, what exactly is being claimed? The second major criticism concerns parsimony. The principle known as Occam's razor suggests that among competing explanations, the simpler one, the one that requires fewer entities, fewer assumptions, is generally to be preferred. Multiverse theories, almost by definition, propose a vast multiplication of entities. Infinitely many universes, in most versions. The response from multiverse proponents is that the theory itself may be simpler, even if the reality it describes is larger, that removing the need for special initial conditions or fine-tuning produces a cleaner theoretical picture overall. But this argument doesn't satisfy everyone. Adding an infinite number of unobservable universes to our ontology strikes many people as the opposite of parsimony, regardless of the theoretical elegance that motivates it. There's also the question of what multiverse theories actually explain. They are sometimes invoked to account for the apparent fine-tuning of physical constants, the observation that our universe's parameters seem improbably well-suited for life. The multiverse, in this role, replaces improbability with selection. Of course we're in a life-permitting universe, because we couldn't observe anything else. But some critics argue that this anthropic reasoning, while logically valid, doesn't actually provide an explanation in any satisfying sense. It tells us why we observe what we observe given that we exist. It doesn't tell us why anything exists at all, or why the mathematics that describes our universe is the mathematics that it is. And the multiverse ideas can differ from each other enormously. Level 1 universes share our physics and our logic. Level 4 universes may share neither. They are not variations on the same theme, they are, in some cases, proposals so different that they can barely be discussed in the same framework. Grouping them all under the label of multiverse theory can create a false impression of coherence, as though there is one unified idea under debate, when in fact there are many distinct proposals with very different theoretical foundations and very different epistemic statuses. Even among physicists who are sympathetic to multiverse ideas, there are significant disagreements about which versions are scientifically meaningful and which have drifted into speculation. The conversation is real, and it is ongoing, and it does not have a resolution. What it has, instead, is a quality that is perhaps more interesting than resolution. It has genuine open-endedness. These are questions that sit at the actual frontier, not the frontier as a metaphor for hard problems with known solutions waiting to be found, but the frontier in the sense of the edge of the map, where the lines stop and the unknown begins. And there is something quietly remarkable about that. About the fact that human beings, on a small planet orbiting an ordinary star in one of hundreds of billions of galaxies, have managed to think their way to questions this large. That the same minds capable of wondering about what to eat for breakfast are also capable of constructing mathematical frameworks that gesture at the possible existence of infinite realities. The questions may never be answered, but the asking of them is, in its own way, something worth noticing. Physics, at its best, is not just a collection of answers. It is a living argument, a conversation between ideas, between interpretations, between people who agree on the mathematics and disagree profoundly on what the mathematics means. And nowhere is that conversation more alive, more unresolved, and more genuinely interesting than in the current debates around the multiverse. We've covered the landscape, the levels, the mechanisms, the philosophical stakes. Now it's worth spending some time with the specific problems that keep the debate honest. Because the multiverse isn't just challenged by the broad objection that it's untestable. There are precise, technical difficulties that researchers are actively working on, and the way those difficulties are being approached tells us something important about where this field actually stands. One of the most significant is something called the measure problem. And to understand why it matters, you need to think about what it means to make a prediction in a theory that contains infinitely many universes. In ordinary physics, probability works in a familiar way. You have a set of possible outcomes, you calculate their relative likelihoods, and you assign numbers, probabilities, that tell you how often each outcome should occur if you repeat an experiment many times. The framework is well defined. The math is clear. But in an infinite multiverse, the usual tools for calculating probability break down in a specific and troubling way. If infinitely many universes exist, and if every possible outcome is realized somewhere among them, then in a straightforward sense, every outcome occurs infinitely many times. How do you compare infinities? How do you say that one type of universe is more probable than another when both types appear an infinite number of times in the larger ensemble? The answer, mathematically, is that you need a measure, a way of weighting different regions of the multiverse against each other, a method for saying that some outcomes are more typical than others even when all of them are infinitely represented. The problem is that there is no agreed-upon way to define this measure. Different choices of measure lead to different predictions. And some choices lead to predictions that are clearly wrong, that say, for instance, that observers like us should be extraordinarily atypical, or that the universe we observe should look completely different from how it actually looks. The measure problem isn't a minor technical footnote. It's a fundamental obstacle to making the multiverse scientifically precise. Without a well-defined measure, it's very difficult to say what a multiverse theory actually predicts, which makes it very difficult to test. Researchers have been working on this for years, proposing different mathematical filters and weighting schemes, checking each one against what we observe, and finding that the problem remains stubbornly resistant to clean resolution. Some approaches work better than others in specific contexts but break down in others. The search continues. Recently, some of this work has taken a new direction. Researchers at UC Davis and elsewhere have been exploring quantum-based approaches to the measure problem, frameworks that apply quantum mechanical reasoning to the question of how to weight outcomes in the multiverse. These approaches are still developing, and their implications are still being worked out, but some of the results are intriguing. Certain quantum treatments of the measure problem imply a different picture of branching and probability than the standard many worlds presentation suggests. They raise questions about whether the branching structure of the wave function is as straightforward as it initially appears, and about how exactly probabilities should be assigned to outcomes in a world where everything happens somewhere. That same body of work touches on a question that has become increasingly active in the physics community: whether many worlds, as usually presented, is really as assumption-free as its proponents claim. The argument for many worlds has always leaned heavily on its minimalism, the idea that it adds nothing to quantum mechanics, that it simply takes the equations seriously. But some physicists now argue that the interpretation carries hidden assumptions of its own, particularly around the definition of probability in an infinite branching structure, and that these assumptions are not obviously more defensible than the assumptions made by competing interpretations. The debate is technical, and it is genuine. It is not a debate between people who understand quantum mechanics and people who don't. It is a debate between careful thinkers who agree on the formalism and disagree on its interpretation, which is precisely the kind of debate that tends to run the longest and cut the deepest. On the question of testability, which we identified earlier as one of the central challenges for multiverse theories, some physicists have pushed back in interesting ways. The claim that the multiverse is inherently untestable is not universally accepted, even among skeptics of the idea. And the arguments for its potential testability are worth taking seriously, not because they resolve the question, but because they show that the situation is more nuanced than it might first appear. One line of argument concerns the cosmic microwave background, the faint afterglow of radiation left over from the early universe, which has been mapped in extraordinary detail by satellites like WMAP and Planck. If our bubble universe collided with another bubble at some point in its history, that collision might have left a detectable imprint on the cosmic microwave background. A specific pattern, a circular or arc-shaped anomaly in the temperature distribution, that would be difficult to explain any other way. Searches for such signatures have been conducted. So far, no confirmed detection has been made. But the search itself is meaningful. It demonstrates that at least some predictions of bubble universe models can be formulated precisely enough to be checked against real data. Another approach involves the statistical properties of our universe's physical constants. If we live in a multiverse where constants vary between universes, and if the anthropic reasoning we discussed earlier is correct, then our constants should be typical among life-permitting universes, not fine-tuned beyond what's necessary, but sitting comfortably within the habitable range. Some researchers have attempted to formalize this reasoning and derive specific numerical predictions from it. The results are mixed. For some constants, the predictions match reasonably well. For others, they don't. The framework is not clean enough to constitute a strong test, but it's not entirely without predictive content either. What all of this points to is a field that is not static. The multiverse debate is not frozen in the state it was in 20 years ago, with the same arguments being rehearsed indefinitely. It is evolving. New mathematical tools are being developed. New observational constraints are being applied. New theoretical connections are being made between ideas that previously seemed separate. The measure problem is being actively worked on. The testability question is being actively refined. The relationship between quantum mechanics and cosmological multiverse models is being actively explored. And among physicists, the range of attitudes toward all of this is genuinely wide. Some treat multiverse models as straightforwardly scientific, as legitimate theoretical frameworks that make predictions, however difficult to test, and that deserve the same serious attention as any other area of theoretical physics. Others treat them as scientific in a weaker sense, as mathematically well-developed ideas that sit at the boundary of what physics can currently address, valuable for the theoretical insights they generate even if direct confirmation remains out of reach. And others remain firmly skeptical, holding that without a clear path to experimental test, multiverse theories belong to philosophy or metaphysics rather than physics proper, however beautiful or mathematically sophisticated they may be. What's notable is that these positions don't map neatly onto levels of expertise or seniority or institutional prestige. Serious physicists at major institutions hold all of these views. The disagreement is not about the mathematics, it's about the epistemology. About what science is and what it requires. About how much weight to give to theoretical elegance when experimental confirmation is absent. About whether the scope of physics should be limited to what can be directly tested, or whether it can legitimately extend to what can be coherently described. These are old questions. They predate the multiverse by centuries. But the multiverse gives them a new and unusually vivid form, because the stakes are as high as they get. The question isn't just whether this or that particle exists, or whether this or that force behaves in a certain way. The question is whether reality, at its largest scale, is something vastly bigger and stranger than the cosmos we inhabit. Whether our universe, for all its billions of light years and billions of years and billions of galaxies, is a small and perhaps unremarkable corner of something that has no edge and no end. That question doesn't have an answer yet. It may not have one for a very long time. It's possible, and some thoughtful people believe this, that it may never have one, not because the universe doesn't have an answer, but because the answer lies permanently beyond what any instrument we could ever build can reach. And yet the question keeps being asked. Keeps attracting the attention of the most careful and creative minds in physics. Keeps generating new mathematics, new predictions, new debates. There is something in the question itself that resists being put down. Something that makes it feel important to keep asking, even without a clear path to resolution. That persistence, That refusal to let the question go is itself something worth noticing. It says something about the nature of curiosity, about the particular kind of restlessness that drives scientific inquiry forward, about the human willingness to stand at the edge of what's knowable and keep looking outward, into the dark, with patience and with care. Skepticism is not the opposite of wonder. It is, in many ways, its most honest expression. To look at an idea carefully enough to find its weaknesses, to hold it up to the light and ask where it fails, that is not a rejection of curiosity. It is curiosity taken seriously. And the physicists who remain unconvinced by multiverse theories are not, for the most part, people who find the questions uninteresting. They are people who find the standards of evidence important, who believe that the discipline of requiring testable predictions is not a limitation on science but its defining strength, who worry that a field willing to accept beautiful untestable ideas as genuine knowledge is a field that has, in some quiet way, lost its footing. That concern is worth taking seriously. It has kept the multiverse debate from becoming purely a matter of theoretical aesthetics, from drifting into a space where elegance substitutes for evidence and mathematical consistency becomes its own justification. The skeptics provide necessary friction. And in a field where the ideas are this large and the experimental constraints are this sparse, friction is valuable. But the conversation has not stalled at this impasse. It has moved. And some of the most interesting recent work is attempting something genuinely ambitious, not just to defend or attack the multiverse as a philosophical position, but to place it on firmer mathematical and physical ground. To find frameworks in which multiverse reasoning becomes more precise, more internally consistent, and more connected to things that can, at least in principle, be tested. One of the most intriguing directions involves the attempt to unify the quantum and cosmological aspects of the multiverse into a single coherent framework. We've been treating these somewhat separately, the quantum branching of many worlds on one side, the cosmological bubble universes of eternal inflation on the other. But some recent theoretical work argues that these two pictures may not be as distinct as they seem. That they might be different aspects of the same underlying structure, and that understanding that structure could resolve some of the deepest difficulties in both. In this approach, probabilities, both for quantum mechanical outcomes and for cosmological configurations, are derived together, from a single framework rather than two separate ones. The hope is that this unification would address the measure problem from a new angle, providing a principled way to assign likelihoods to different outcomes across the entire multiverse, quantum and cosmological alike. Instead of patching quantum mechanics and inflation theory together after the fact, the idea is to find the deeper mathematical ground on which both of them rest. Whether this program will succeed is genuinely unknown. It is active work, at the frontier, and its conclusions are not settled. But the fact that it is being pursued, that physicists are looking for this kind of unification, reflects something important about where the field is headed. Not toward acceptance or rejection of the multiverse as a whole, but toward a more precise understanding of what the various multiverse proposals actually claim and how those claims connect to each other. Part of this work involves a concept called the causal diamond. It's a technical idea from general relativity and quantum gravity, but its essential meaning is accessible. A causal diamond is the region of spacetime that a given observer can, in principle, both influence and be influenced by. The complete set of events that fall within that observer's causal reach, bounded by the limits set by the speed of light and the structure of spacetime. It's a way of defining what's real and relevant from a particular perspective, rather than from some hypothetical view from outside. Some theoretical work on the multiverse has started using the causal diamond as a fundamental unit of analysis. Instead of reasoning about the entire infinite multiverse at once, which is where the measure problem bites hardest, this approach focuses on what can be observed and inferred from within a finite, causally connected region. The idea is that physics should be formulated in terms of what observers can actually access, not in terms of an infinite background that no observer could ever survey. This is connected to a broader shift in how some physicists think about the relationship between observers and the physical theories they construct. The traditional picture treats the laws of physics as existing independently of any observer, as descriptions of a reality that would be the same whether or not anyone was there to measure it. But in the context of quantum mechanics and cosmology, where observation plays a fundamental role and where the limits of any observer's causal horizon are physically significant, some theorists argue that observer-based reasoning needs to be built into the framework from the start. Not as a philosophical addition, but as a structural feature of the theory. The causal diamond approach tries to do exactly that. It takes seriously the idea that what we mean by the state of the universe is always the state as seen from somewhere, from within a particular causal region, and it asks whether a consistent and predictive physics can be built on that foundation. Early results are suggestive, though far from complete. Within this framework, the cosmological constant, that number governing the large-scale expansion of space, whose observed value is famously difficult to explain from first principles, takes on a new significance. The cosmological constant has long been one of the central motivating puzzles for multiverse thinking. Its observed value is extraordinarily small compared to what naive quantum field theory would predict, a discrepancy of many orders of magnitude that remains one of the most embarrassing gaps between theory and observation in all of physics. The multiverse offers one possible explanation: if the cosmological constant varies between universes, and if a larger value would cause space to expand too rapidly for galaxies to form, then observers like us will only ever find themselves in universes where the constant is small. Our measured value is small not because of some deep physical principle, but because we couldn't exist to measure it if it were large. Some of the recent theoretical work connecting multiverse reasoning to the causal diamond framework has revisited this explanation and found it more nuanced than the simple anthropic story suggests. When you take seriously the observer dependence of the causal region, and when you ask what a typical observer in a universe with a given cosmological constant should expect to see, the predictions shift in subtle but potentially meaningful ways. The framework doesn't yet make sharp enough predictions to constitute a strong test. But it is sharpening. The mathematics is becoming more precise. The conceptual foundations are being examined more carefully. And underlying all of this, the measure problem, the causal diamond, the cosmological constant, the unification of quantum and cosmological multiverse reasoning, is a deeper question that all of these approaches are, in their different ways, trying to answer. What is the correct way to reason about a universe, or a multiverse, that is larger than any observer can see? What does probability mean when the ensemble you're drawing from is infinite? What does it mean to say that our universe is typical, or atypical, among all possible universes, when we have no way to survey the full distribution? These questions are not just technical. They touch on the foundations of scientific reasoning itself, on what it means to have evidence for a theory, on how much weight theoretical elegance should carry when direct observation is impossible, on whether the goal of physics is to describe what we can measure, or to describe what is, whether or not we can ever reach it. There are no settled answers. There may not be settled answers for a very long time. But the work continues, and it is serious work, done by serious people, with genuine care and genuine rigor. The multiverse has not been proven. It has not been disproven. It lives, as it has always lived, at the edge of what physics can currently say, a region where mathematics and imagination and careful argument are the only tools available, and where the questions are large enough to last a lifetime. And so we arrive at the end of this long, quiet journey through some of the most extraordinary ideas in all of human thought. We started with a simple observation, that our universe might not be alone. That the cosmos we inhabit, for all its staggering size and beauty, might be one small piece of something inconceivably larger. We followed that idea through its many forms, through infinite space and bubble universes and quantum branches and colliding brains and mathematical structures existing in their own right, and we watched it grow stranger and more ambitious with each step. We also watched it encounter honest resistance. From physicists who ask for more than elegance. From the measure problem, which reminds us that infinity is not a number you can calculate with carelessly. From the testability question, which reminds us that science is not just about what can be imagined but about what can be checked. These challenges are not signs that the multiverse is wrong. They are signs that the question is genuinely hard. And hard questions, pursued with honesty and patience, are where the most interesting knowledge eventually lives. The scientific theories of parallel universes remain unproven. They may remain so for generations. But they represent something remarkable about this particular moment in the history of human inquiry, a moment when our mathematical frameworks have grown powerful enough to gesture at realities beyond any horizon we could ever cross. When the tools we've built to understand the world we can see have begun, almost despite themselves, to describe worlds we cannot. Whether those worlds are real is a question the universe has not yet answered. But the asking of it, the careful, rigorous, imaginative asking of it, is itself one of the most extraordinary things our species has ever done. To stand at the edge of everything we know, in the quiet of a late night, and wonder whether the darkness beyond the last visible star contains not emptiness, but everything. That thought is worth carrying gently into sleep.